Okay, so we left here last day where we discussed like how by starting from an anchor point we can design an explanator which will explain with uh, some confidence as to uh, what is going on in the inner workings of the model. And from there also we saw some interesting insights were obtained by the authors, and like we stopped at the point where we say that one can also uh, carefully select multiple anchor points so that they are diverse in nature in the first place, and the second thing is that uh, the redundancy is minimized when you choose multiple anchor points. Okay, so that was the objective. So as we say, so uh, uh, beyond explaining single predictions, now we move to the paradigm of explaining the whole model, the functioning of the whole model. And how do we do that? So basically, as we said, as we agreed, that explaining one prediction actually kind of gives you an idea of a local behavior of the model. However, if we can very cunningly pick k such predictions, then we might be able to describe the overall behavior or explain the overall behavior of the model. Okay. Now, as I was telling you earlier also that it is very difficult to avoid redundancy if you pick these k predictions say randomly. Okay, so if you do that randomly, so then it's going to be like there is a high chance that there will be um, the points that are chosen are redundant. So the authors develop a heuristic algorithm in order to increase the diversity of the points and reduce and thereby reduce the redundancy of the points that are chosen like as exemplars for constructing the explanator. Okay. So the idea again is like you have say this is the whole space of your data, and you have one explanation example like that as shown in the figure, and then you try to select other anchor points or exemplars at like uh, um, uh, at distances so that they are not very close to each other and they represent a diverse set of anchor points which can possibly explain the behavior of the model better. Okay, so we will start with like a small intuition as to how this submodular selection of the samples um, goes on. Okay, so we want to understand like how the authors went on to do this submodular selection. So let's say that we have some documents. Okay, they are numbered from 1 to n. Okay, so these are n's documents, and these are features representing those documents. Now in this case, like as you can understand very well that the features are unigrams. Okay, so we represent the documents using unigrams. So there could be various other ways of representing features, as you can well understand, but this is a very simplistic example to give you a flavor of the selection algorithm that they are going to design. So let's say you have these n documents and some d prime features. Okay, so the feature runs from j equals 1 to d prime, and the documents are indexed as 1 to n. Now say the for the sake of simplicity, let's say that this gray boxes actually represent 1 and these white boxes represent 0. For the time being, let us go with a 0 1 matrix. Okay, we will see later on how to exactly fill these boxes, but for the time being, let us assume that for our understanding purposes, let us assume sorry let us assume that these are like zeros and ones. So, the gray boxes are ones and the white boxes are zeros. Now, from this, uh, can you tell me like uh, anything peculiar about this matrix that immediately comes into your notice? Nothing is very peculiar. Something that immediately draws our attention. So, a standard guess would be the feature F2, okay, the feature F2, fine. So, this feature seems to be spanning across 4 out of 5 documents, okay. Out of these 4 documents, out of these 5 documents, 4 have this particular feature, okay. So, then if I have to pick up points, okay, or documents that increases the diversity, or in other words reduces redundancy, what could be my policy from this observation? Think aloud, because most of the questions that you face in this type of like problems is like related to thinking, more thinking than writing.
So F2 is not a very useful feature in that case.
Is that so? I mean, will you? So I guess this is hard disk, right?
Yes, sir.
So think your task is to select documents. We are trying to internally see the features, that's fine. But finally, you will have to find out a set of exemplar documents, which together will build a nice explanator. You have to select documents judiciously. Okay, let me give you a hint. Say I choose, let me call this document 1. Okay, I choose document 1. So I am allowed to choose only 2 documents. My budget is that I can only choose 2 documents out of this 5. I cannot choose more than that. Okay, I will have to choose only 2. If I choose document 1 and say document 5, will that be a good choice? What is your intuition? So what should be the documents able to do? Where are we going at? What should be the documents that I am choosing be able to do? these documents should be able to maximally cover the important features, right? Because if you can cover the important features, then the explanations will automatically come from those features. For instance, Christ is an important feature here. Okay, so if I can include documents which has this feature, fine. So I'll have to maximally I'll have to include documents in such a way that it maximally includes the different features or the different features as per their importance. Now, if I tell you this, which two documents would be your most preferable ones? They will be sufficiently diverse, but at the same time, they will include most of the information about the features. Now,
D2 and D4.
D2 and D4. Okay. Why do you say so, Hardik? Can you give us a little bit of intuition? I'll tell you. You are very correct. Can you give us an intuition as to why you thought this?
So because if you look at the number of covered features, F2, F3 and F4, like these three features occur kind of maximum number of times, and if we choose D2 and D4, we cover all of these three, like the union of features covered becomes F2, F3 and F4.
Acha. Let me give you another choice. D2 and D5. What about it?
So D2 and D5 covers actually more number of features, but like our
They
aim
are
was to cover F2 more number of times, right?
no, not F2 more number of times. Our aim was to include F2 somehow.
Okay.
Because F2 is important, F2 has to be included. Basically, think of this as including documents in such a way that I prioritize the inclusion of certain features over others. Now, if I have a budget on top of this, which documents should I include?
D2 and D5 are a better option in that case, I
D2 and
guess.
D5 are
Yeah.
better options, right? Everybody in the class agrees with the intuition that Hardik presented and that we talked. Okay, let me see how many raises hand. Because this is an important thing. Why I'm harping on this? Because you might get this kind of questions. Oh, I don't see anybody raising hands. Let me raise my hand at least. So nobody agrees. Okay, I have got 3, 4, 5. Okay, pretty decent. So I guess more or less all of us are agreeing on this. So then we can proceed forward. Okay, so we were here. Now, how to compute these? Which documents to include? How do I computationally find this? Okay, so this we were given an example. We did some hand coding, and from there we kind of identified that okay, D2 and D5 should be the documents which would more or less include all my features except F1. So it will cover like F2, F3, F4, F5, and probably will be able to generate the most varied set of explanations compared to any other documents that are present here. Like if I am asked to uh, like return back 2 documents which should be included, then this should be my answer. Okay. So by the way, Hardik, so if D2 and D5 is a good choice, then D3 and D5 is also a good choice. Okay. So these two are equivalently good choice. Any one of them is fine. You see their coverage is very similar.
Yes, sir.
Yeah. So now how do you do this? So in order to do this, we compute a um, uh, like a metric called ij, which is an importance associated with the features. Okay. So as you see, it runs over j. So j equals 1 to d prime. Now you try to compute the square root of sum of wij's. Okay. Now I runs from 1 through n. So basically you are computing the importance of this particular feature across all documents, importance of F2 across all these documents, importance of F3 across all these documents, etc., etc. Okay, so in this way you are computing the importance value of a particular feature across the documents. So this is kind of, you can think of a column wise sum of the matrix and a square root of that. Okay. So now of course, like as you can well understand that F2 can be used to explain more instances and this comes directly from the fact that I2 is greater than I1. Okay. Now you can compute all the I values from I1 to I5, fine, and then like you can order them based on their importances. So this is one part of it. Now I have the task of, so here the important thing is my unknown is this V. So this V is the documents that I am going to pick up. Okay. I am going to pick up a set of documents, fine. From this whole set of documents that I have, I am going to pick up the documents such that the coverage of the important features is maximized. Okay. So this is what is being done here. So you sum the importances. This one is an indicator function and like it is 1 when this I is part of V. This particular document has been chosen and the wij value is greater than 0. Okay, for this time being we have taken zeros and ones. So say for instance, like in this case you can assume that wij is equal to 1. Only when wij is equal to 1 and you have chosen that particular document, okay, you can set the indicator function to 1 and the importance gets added. Okay. Now you have the task of finding the V that maximizes this value. Okay. That actually increases the coverage. Fine. Given W and all the important scores, I want to find that set of V's where my coverage or this particular function is, or this particular metric is maximized. Okay, that is what is my task. Now the question is like V is not unconstrained. Okay, as I was telling you that there is a budget on V. Okay. So V is less than some value capital B. So for instance, as I was telling you in this particular example, you are allowed to choose only 2 documents out of 5. So such a budget is given to you. Given that budget, you want to find the argmax of C, and that is done by an algorithm which they call the pick W comma I. So this is a submodular optimization that they solve. Now what do they do basically? So they have this particular coverage value, right? So you start with some V. Now you include a particular document and you see the difference in the coverages. Okay, what was the earlier coverage and what was the new coverage? So you start with some XYZ, like one of the random documents, say like any one of the files that you have seen earlier. You start with that. Now you include one more document, okay, and you see whether there is a difference in the coverage that is positive, okay, and you keep on doing this until and unless your budget is exhausted, fine. So now, so this is called the marginal coverage gain. So how do you solve this optimization problem? You use a submodular optimization technique so that like the gain actually goes down over iterations. So basically, like in the earlier iterations, you have larger gains, and slowly the gain falls as you increase the number of iterations, and at some point in time the gain will be very, very low, at which point you can assume that a convergence has been reached, okay, and uh, a convergence has been reached, and uh, at that time, so this submodular optimization technique that the authors use actually is adapted from this paper Krause and Goldwyn, 2014, which guarantees that the results that you get is within 1 minus 1 by E constant factor of the optimum value that you could have achieved. Okay. So this algorithm that they are using, this is not their own. This optimization that they are using is borrowed from an earlier paper. Only the coverage metric is defined by them. Okay. The coverage metric is defined by the authors. Okay. And like if you use this submodular optimization, since this function itself is submodular, you can use this submodular optimization, and whatever final values you arrive based on this submodular optimization is guaranteed to be within 1 minus 1 by E of the optimum result. Okay, so roughly this is the algorithm. So you start from, so this I have already showed you. You start from j equals 1 to d prime, and you compute the importance values of each of the features, and then you start with an empty set, and then you do a greedy optimization. You start including one by one the documents, and every time you compute the gain, and you keep on computing the gains until and unless there are no further gains possible over iterations. And at that time, like whatever the set V is, you return that back to the user. Okay. So now there is of course a fixed budget up to which you are allowed to do this inclusion of V's. Fine. Now there is only one part that is left. How do we fill up these boxes? Okay, each of these boxes, how do we fill up? Do you see a clue in this algorithm as to how this is being filled up? There is a hidden clue. This part I have already told you. Once the matrix is filled up, this part is understandable. You compute the importances, and then like you compute the difference in coverages, and you maximize the coverage until and unless your budget is exhausted. Where do I get the initial entries in the matrix from? Are you seeing this? What is your best guess? What is this? No idea. These are the single point prediction weights that we learned when we were discussing about the single point line or the single point explanator. So there was this single anchor, right? For a particular anchor chosen, you found out the weights of the surrounding points. Okay, those weights are pumped in to the WIs. Fine. Now these are used to populate. So those are like the initial approximate very crude values of W that you are using, like say you take some n number of anchor points initially, and you compute the weight values for each of the random additional points that you are picking up around that anchor point, and you are computing the weights from this anchor point to those points. So these weights are actually stored with you. These single prediction weights are stored with you. You bootstrap your peak algorithm with these single point weights, okay, or these single prediction weights. Now once you have this, you start your algorithm, you start your submodular optimization algorithm in the hope of getting better and better instances. Okay. So that's how you generalize from that very specific algorithm of single point prediction explanations, you generalize into a whole model prediction explanation. Now the authors went on to evaluate also the whole model explanations. Let's see how they did it. So one of the tasks that they set for was to choose between competing models. Okay. So given two different ML models, using the explanation, can I choose which one should be, like, deployed? So given the task that I have two ML models, ML1 and ML2, I do not know like how they internally work, but then I can look at the explanations, and looking at the explanations, can I tell like which one of them should be deployed in the wild? This is one task that they set for. Okay. So what they did was they asked uh, empty workers, in order to find out, say given a pair of models, they asked the empty workers which they felt actually generalized better. Fine. So that was the task that they set for. Think of this. So you have two such ML algorithms, both of them are black box. Fine. Both of them are making correct predictions that this is related to atheism. Okay. So both of them are giving correct predictions that this particular news group post is related to atheism. The same example that we were looking at yesterday, we are continuing with that. So both of them give correct predictions, but the explanation to their predictions are different. Okay. So one on the left hand side gives certain words which the algorithm feels is most important in order to predict that this particular news post is related to atheism, whereas there is the other one which gives stress to some other words, which makes the algorithm detect it to be belonging to the atheism class. Now which one do you think is more believable or more deployable? So like imagine that you are also a empty worker at this point. Which one would you choose as a more generalized model? Which one is picking up more representative keywords? Left or right? No clues?
Left.
So to me it appears that left is more uh, appropriate, because simply because of the reason that the right seems to be picking up artifacts like posting, host, and NTP. These are like not even part of the message. Okay, so these are, so it's picking up certain things which are like kind of um, like artifacts, useless signals, okay, in order to detect something to be uh, in the atheism or Christianity class. Okay, so in this way they were given multiple such pairs of outputs from different algorithms, and the Tarkers were asked to rate which one of them they found better. And what they uh, found was that the better model was chosen by the Tarkers more accurately when they saw the explanations given by the Lime submodular algorithm. Lime random is the the anchor based algorithm, like you have the single anchor and then around it you devise Lime. And the Lime submodular is like where you are doing a whole model explanation, and this is by random guessing. Okay, so they are the Tarkers are not given any explanation. They are just shown two outputs of the algorithm side by side, and they are asked that which one do you think is a better model or a more suitable model for deployment. The second one, they were provided with the explanations from the Lime explanator, like using the single point prediction multiple times. And the third one is like they were given explanations generated by the Lime submodular algorithm, that is the peak algorithm. And what you see is that the um, users are successful in picking up the better model uh, like more accurately when you are given, when they are provided with the explanations from the Lime submodular. So the next task that they set on is to fix bad classifiers. So I was telling you last time also, right? Last day when we were discussing, we saw that how these explanations can help us further like fine tune the model and give it better clues, so that the subsequent predictions that are made are like more accurate or more appropriate. So the authors went on to do this. So uh, that is what is being shown in a small block diagram here. So you train the model with the 20 news groups item, then you test it with the 20 news groups item, then you use an explanator which gives you the explanations, and then you again recruit mechanical Turk workers to identify whether the explanations are good or bad. So now the Turkers are asked that if you find certain explanations are inappropriate, just strike them off. Okay, and this struck off explanations, okay, are fed back to the model, and the model is retrained, okay, with the additional clues that it gets from the Turkers. And then like once this retraining is done, so you keep on repeating this like over multiple cycles you keep on repeating this, and then after some point in time you see that the accuracy kind of saturates, and at that time if you are evaluating with a completely hidden data set, okay, which has nothing to do with this 20 news groups training and test data, you see that the performance is much better. Okay, so this is what the, yeah, the Turkers don't know about this data set at all. So so what do they do? So suppose you have the, so the Tarkers are presented with this kind of a view. So on one side is the explanation from the Lime submodular algorithm, and on the right hand side is the post from which the explanations are generated. Now the Tarkers are asked that if you find certain explanations to be useless, please strike them off. Okay, that is what the Tarkers are asked to do. Fine. So the true class is atheism, that is also told to the Tarkers, and the document is provided, as well as the explanations as to the classification made by the model are also provided. Now the Tarkers are asked that you strike off those which you do not find relevant in the classification, and so the annotation portal allows them to do this striking off, and once this striking off is done, this input is sent back to the model, and the model is retrained. Okay, and what you see is the following. So if you train on this 20 news groups data and you test on a hidden set, on an unknown set, okay, then if you are doing it completely like in the wild, then the accuracy stands to somewhere around 57%, as you have seen. Okay, if you hand clean the data somehow, okay, so you look at the training examples painstakingly and you try to clean the training examples, like try to give additional markers so that the training data does not pick up like artifacts, even then with all these efforts you can reach an accuracy close to 70%. However, with the Tarker's help, over rounds, as we have said in the previous slide, this repeats, right. So this repetition, as you see, after 3 rounds of repetition, we are already able to reach an accuracy of around 75-76%. Okay, this is on the data that has been cleaned by the Tarkers through the like striking off of the explanations that they were presented in an annotation, in a suitable annotation platform. Okay, so in this way the Tarkers over rounds enriched or cleaned the 20 news group data, and based on this cleaned data, when the model is retrained, the performance on the hidden data set, on the hidden uh, religion data set, which the Tarkers had no idea about, as well as the model is not trained on them, even then the results go up to 75%. And this now depends like how much money you have, and how much accuracy requirement you have. According to that you can proceed across the rounds, but after some time we will see that this will saturate. Already there is a saturation trend, and after some time, say like in another 1 or 2 rounds, things will saturate to something around like 80% or something. Okay, so depending on the investment, depending on the accuracy requirements in the like wild, you have to say, you have to choose the number of rounds that you want to go for, because every round has a cost and time associated with it. So this kind of roughly gives you an idea of how explanations in machine learning model can be obtained in the first place using algorithmic techniques, as well as can be used to further refine the performance of standard machine learning classifiers. Okay, so this is a classification stage setting. Similar models have been, similar like tasks have been done on regression settings and other types of machine learning tasks. Like there are a lot of references, and if you are interested, like we can catch up at some point in time. In fact, we ourselves are also working in this area, trying to compute something called influence functions and how they help in improving the model. So influence functions are also a type of explanators. So starting from the days of Lime in 2016, a lot of different types of explanators have come into the market, and even now this is a very hot topic of research. And if you are interested further, so this actually is dealt in predominantly in the NLP literature, and if you are interested in more details, like we can catch up sometime to discuss further. Okay, so this was all about explanations. So we will uh, quickly now move into the last part of our syllabus, which is about media bias.